today is I want to talk more about Cauchy's theorem. So we mentioned Cauchy's integral formula last time. So right now, who's winning, Cauchy or Riemann?
Cauchy.
Cauchy. We haven't even heard of Riemann yet. Right. We will hear of Riemann later, but this is the Cauchy part of the course. So f is holomorphic on disk. F of z is 1 over 2 pi I, the integral over some circle of f of zeta over zeta minus z is zeta. C is a circle containing z. So I just want to make sure always when we do complex analysis, we always want to work in open sets. We're going to work in an open disk. We'll take some circle, we'll take some point z inside the circle. And what we're saying is that if we integrate along the boundary of the circle, that recovers the value of the function here. This is absolutely amazing. What this is telling us is that if I want to specify a complex function, if it's differentiable, all I need to do is tell you its value on the boundary, and everything else fills in. What should be really going on in your mind is the Cauchy what? Which equations? Yeah, so Riemann does actually get some notice today. The Cauchy-Riemann equations are lurking in the background. If a function is differentiable, if it's complex differentiable, you have these conditions on the real parts and the imaginary parts. You have the relations between their partial derivatives. Think now of a differential equation. I have specified my boundary conditions, and I'm specifying how they're changing in x directions and in y directions. And that's going to uniquely fill it in. Now the miracle is that if I specify it on the boundary, there is a way to consistently have it fill in. That's not always clear. You cannot just choose willy-nilly, that's a technical term, what you want the values to be on the boundary.
Hello.
Hello.
Can you have the class with that drilling?
I'm sorry, I can't hear you over the drilling.
I'm going to call about it, but...
Yeah, if you can call about that, that would be great. But we'll just have to be even more excited about complex analysis today. And I do feel sorry for the people who were complaining about the audio in the video the last lecture. They now have this stuff. Maybe that's what happened. Right. So you can't just put in any values you want on the boundary. But if the function is holomorphic, you can't. Now again, if you're saying holomorphic, it should really be giving you maybe some little neighborhood around the circle where the function is defined. But you can, of course, just look at it being viewed there. Alright, so this is absolutely amazing. This formula is going to have an immense number of consequences. One of the big ones, as a corollary, is this is almost an English result. Holomorphic equals analytic. That if a function is complex differentiable, it has an infinite Taylor series expansion which converges. The other direction is no problem, because if you have an infinite Taylor series that converges, then you can differentiate inside the circle radius of convergence. Okay. So what we want to do now is we want to prove why this formula holds. Right. Let me close the door because between the drilling and other colleagues lecturing, it's going to be too difficult. Right. So proof. So what we want to do is we want to prove a formula like this. When you look at the function f of zeta over zeta minus z, we're integrating with respect to zeta. Is this a good function or a bad function? So when we're looking at the function, I went over 2, once I go over 2, it doesn't like it. Right. So when we're looking at the function f of zeta over zeta minus z, is this a good function or a bad function?
As long as zeta isn't on the boundary of a circle, which is in the circle, it's not, we're okay.
As long as what?
Z.
As long as z is not on the boundary of the circle. So the only place where this blows up is at z. So what we can do is, this is the original contour we're given, and say, let's say this is the point z, and here's zeta living on the boundary. What we want to do is we want to integrate holomorphic functions over nice regions, because the integral of a holomorphic function over a nice region is 0. So what we're going to do, is the following. We're going to go around the circle, and then we're going to head in and go around the point Z, and then we're going to head out. And I'll give a pretty close sketch of this. You know, the full details are in the book. Is this the right way we want to integrate around this point? Do we like integrating clockwise? No. We always define our integrals to go counterclockwise. Well, that's great. If this integral is going clockwise, that's really counting it as a negative. This integral over here is going in the correct direction. In the limit, as this thickness goes to 0, what happens to those two integrals over these two lines? They cancel. And so in the limit, as this thickness goes to 0, these will cancel, and this will converge to the following. And we'll be integrating over something like this. Okay? What would be the integral of our function over this region? This is our chance to answer. We have no buzzing right now. 0. Good, thank you. Excellent. It would be 0 because our function is holomorphic. F of zeta over zeta minus z is holomorphic. So whenever you see math, you always want to think about notation. Why are we using zeta as our variable? We've been using z as our variable every place else. Why did we switch to zeta? Unless you're new to the class today, in which case it doesn't really matter to you because you haven't seen any of it. Why are we using zeta for a variable of integration?
Because z is already used?
Yeah, we're trying to write our function f of z, so z is already used, so we've got to use something else, so we'll use the Greek letter, zeta. And so at the end of the day, we want to talk about finding our function, the initial function at a point z, so we're saving z for that. We will use zeta for the dummy variable of integration. Z is fixed. We are in a region where zeta minus z is never 0. We are bounded away from here. This will have some small radius epsilon. So in this region, f of zeta over zeta minus z is holomorphic, so the integral is 0. As I take the limit, as this thickness goes to 0, I will be left with a circle of radius epsilon about z. Because it's going in opposite orientation, the integral of this plus the integral of this is 0, so the integral of this equals the negative of the integral of this. And when I take the negative of that, I've now restored the correct order of integration. And so we get that the integral along the big circle of f of zeta over zeta minus z d zeta equals the integral, let's call it the circle of radius epsilon, of f of zeta over zeta minus z d zeta. And now we've restored the order of the integration. We're now going through this clockwise. Well, this is pretty good. This is almost, in fact, what we want to integrate. It's just missing a 1 over 2 pi I. We can divide by 2 pi I later, not a problem. Now we're left with this integral. What's the problem with this integral?
It blows up.
Yeah, it blows up. That's kind of bad. Except in complex analysis. In complex analysis, you like blow-ups. That doesn't mean you like it when I explode and start yelling at you, throwing chalk and whatnot. But when your function blows up, you exploit it. Everything in complex analysis comes down to exploiting the blow-up. But we have to do it in a very nice way. So we know how to integrate the function z to the n. If n equals -1, we get a nice contribution. If n is not -1, we get 0. What we want to do is we want to rewrite this in such a way. And what we're going to do is, I'll first put in the 2 pi i's, just to have them throughout. And now we get it's 1 over 2 pi I integral over c epsilon of f of zeta minus f of z plus f of z over zeta minus z d zeta. So we've done one of the few things we can do in mathematics. We've done nothing. Right? There are 2 ways to do nothing. You can add 0, you can multiply by 1. You need to get proficient in this. In fact, I just got an email from one of my students who's in Budapest who thanked me for teaching him how to do nothing for so many classes. It's been extremely useful in the combinatorics they're doing. Why would we want to write something like this? We have a zeta minus z. As zeta goes to z, this is going to 0, this is a problem. Well, since my function is continuous, if I look at f of zeta minus f of z, that will go to 0, that will cancel with this. And now this will be well behaved. Now we can actually do a lot more. Because the function is differentiable, f of zeta minus f of z over zeta minus z, that's going to be a nice number. We actually don't need the full strength of that. All we need is that this quotient is bounded. Because what's the perimeter of the circle? That's going to be on the order of epsilon. 2 pi epsilon if you want to be exact for what the perimeter is. As long as this quotient is bounded, the contribution will go to 0 as epsilon goes to 0. So the question is, do we actually need f to be holomorphic for this argument to work? Where did we use holomorphicity? Are we only using it here, or do we use holomorphicity in some other place? Let's move back here. So where did we use holomorphicity?
Say that the integral along closed curve was...
Yeah, to say the integral along the closed curve is 0. So even though we don't need holomorphicity in the later part, we did use holomorphicity essentially over here. So it's always good to keep track of what we need. If we knew that the integral of f along closed curves was 0, then we would be fine and we would not need anything further. Yes?
This is just a definition refresher question, but is it still holomorphic even if it blows up at that point C?
Well, we were looking at a function that was holomorphic in an open set.
Okay.
And so remember, the important thing is we're choosing a circle of radius epsilon, so we are staying away from that point Z. Epsilon can be damn small, but it is not 0. And so we are staying away from it, and in that region, it's fine. In fact, the function will be even bounded in that region. Now, as you take the limit as epsilon goes to 0, your bound is going to have to get larger and larger and larger, and it will blow up. But as long as we keep epsilon fixed and positive, we have a region where the function is holomorphic, and we can then use our results.
But in the C epsilon...
In the C epsilon, this function is not holomorphic. Correct. But if we look at this new function is fine. Why is this new function fine? Because zeta is on the boundary of the circle of epsilon. Zeta is never equal to z. So because it's never equal to z, we're never actually dividing by 0. We're close. So what we now have is we have 1 over 2 pi I, the integral over c epsilon of f of zeta minus f of z over zeta minus z, plus 1 over 2 pi I integral over c epsilon of f of z over zeta minus z d zeta. And I'll put in the d zetas to remind ourselves we're integrating over. Right. So we've talked that this integral goes to 0 as epsilon goes to 0. And it's because f is continuous. That's all we really, well, we need a little bit more than continuous. Lipschitz, I guess, since f is holomorphic, that would be enough to give us that this quotient is bounded. If you know what a Lipschitz condition is from analysis, being Lipschitz is enough here. All right, now let's look at this piece. What do you want to do for this integral? So which integration law do you want to use? We've got an integral of f of z over zeta minus z d zeta.
Parts.
Not parts.
Substitution.
We'll eventually do substitution, but there's something you should do first when you see an integral like this. What's the first thing you should do?
Pull out f of z.
Pull out the f of z. F of z is a constant. So this part over here is 1 over 2 pi I. Okay, I'll write it this way. I'll pull out the f of z, and then have a 1 over 2 pi I integral over c epsilon of 1 over zeta minus z d zeta. And now we need to figure out how to evaluate that integral. So we can write zeta minus z is epsilon e to the I theta. D zeta is going to be epsilon e to the I theta I d theta. And so now we have it equals f of z 1 over 2 pi I integral theta goes from 0 to 2 pi. We have a 1 over zeta minus z, so it's epsilon e to the I theta. The d zeta becomes epsilon e to the I theta I d theta. The epsilons cancel, the e to the I thetas cancel, the I cancels with the I over there. we integrate from 0 to 2 pi of the function that's identically 1, we just get 2 pi, and we just get f of z, which completes the proof. So it reduces to that one integral I said we need to know. We need to know how to integrate the function 1 over z. Now today, of course, it was written as 1 over zeta minus z, but it's still the same integral. Right. Because I'm teaching at Williams, it's worth mentioning we have two colleagues who often fight and have arguments. Who are the two colleagues? Garrity and Adams, and they have debates on lots of issues. They've had the Euclidean algorithm versus... Exactly. It shouldn't even matter what you put the Euclidean algorithm against. Hands down, Euclidean algorithm should win. I'm sorry, Professor Adams. They've had E versus pi, but that's the wrong debate. The debate they should have is not E versus pi, but pi versus 2 pi. And if you want to allow third-party candidates, you can allow 4 pi to get to the stage. In complex analysis, which is the more important number? Pi, which is coming from the area of the circle, or 2 pi, the perimeter of the circle coming from line integrals. So one of my professors once said if the Greeks were really intelligent, they would have invented the constant 2 pi. And it is worth thinking about which is the more fundamental quantity. In complex analysis, 2 pi is showing up all the time. It is a bit much to ask the Greeks to have invented 1 over 2 pi I, or 2 pi I. That's fine. But 2 pi, you can make a legitimate case. And there are people who celebrate 2 pi day. It's called, what day? Anybody know? Tau Day, exactly. And so maybe we will celebrate Tau Day this year if SMASAB can get its act together. Okay? Anybody know why 4 pi can be a third-party candidate and can come into the discussion? Where might 4 pi come into play?
Electricity and magnetism.
Electricity and magnetism. When you look at what's going on in physics, you have the 1 over 4 pi epsilon naught. And it's really coming from the surface area of the sphere looking at fluxes. Now, my feeling to just completely destroy third-party candidacy right now, once and for all, is that as soon as you start doing to that, well, now you have all these other dimensions you can have into play, and we should really keep it to pi versus 2 pi. Keep the fight clean. Okay. So this is Cauchy's integral formula. It is absolutely amazing how many consequences we have of Cauchy's formula. So the first one is we have proved that this exists, that this is a representation for the function f of z. What would you like to do now? F is holomorphic, so what do we know since f is holomorphic? Holomorphic means?
As a primitive.
Okay, that's a big thing that it has a primitive, but holomorphic means? We don't know analytic yet, but that's what we're going for, that's what we're gunning for. Holomorphic means it is? Somebody translate the word holomorphic. We have complex differentiable. It's complex differentiable. What's the derivative of f of z? Give me the trivial answer, the smart-ass answer. F prime of z. Right, the derivative of f of z is f prime of z. What's the derivative of the right-hand side? What's the derivative of the integral? Is it the integral of the derivative? Wouldn't it be nice if the derivative of the integral were the integral of the derivative? And then you would have an expansion for f prime of z. To some extent, if we knew f prime were holomorphic, we could then use this formula with f prime and maybe deduce things. So what we want to do is we want to see how far can we push this. Can we get a formula for f prime, for f double prime, for f triple prime? If you just push the derivative through the integral sign, we're fine. And we actually get a formula. When we do that, we'll get 1 over zeta minus z. We're taking a derivative with respect to z. We'll get a negative 1 coming from this, but then we'll have a negative from the negative z. The negatives cancel. And when we keep taking derivatives, so we get, as a corollary, the nth derivative at z is n factorial over 2 pi I, the closed integral over c, f of zeta over zeta minus z to the n plus 1 d zeta. Proof. We're engineer hat, and then say the derivative of the integral is the integral of the derivative. Okay? And that's the fastest proof. It is unfortunately not a valid proof in this class. How do we prove it? How do we give a valid proof of this? How would we prove this? So one thing is, I can cross my fingers and hope that you have taken a really good real analysis class where they have given you conditions on when you can interchange differentiation and integration. I'm not holding my breath. Or even if you've seen that you remember it. But that's one way to go, is to actually formally justify when you can do that. What else could we do? How else could we prove something like this?
Perhaps prove that f to the n is holomorphic, and then use Cauchy's formula with f to the n.
So to prove that f to the n is holomorphic, we would have to prove that it has another derivative. And so how do we prove something has a derivative? So we could try to ensure the Cauchy-Riemann equations hold. So sometimes, it gets hard to remember how you do these things. In calculus, how did you prove all these differentiation laws? What did you always go back to? The definition of the derivative. We'll go through by the definition of derivatives. So, proof. Definition of derivative in induction. If you want, I will just prove that f prime exists and is given by this formula. The rest follows similarly. Or if you want, I'll do the general case. It doesn't really make much of a difference. I'll assume we'll do it by induction. So base case is done. Assume true for n minus 1. And the base case is what we just did. So now we look at fn of z is the limit as h goes to 0 of fn minus 1 of z plus h minus fn minus 1 of z all over h. So we go back to the definition of the derivative. And now we can begin to see why this integral formula is so nice. What we now get is the nth derivative at z is going to be n minus 1 factorial over 2 pi I, the integral over c of f of zeta over zeta minus z plus h minus f of zeta over zeta minus z d zeta. And then I have to remember to put these to the right powers. This is to the n minus first power, and this is to the n minus first power. And now you can see why I wanted to just do maybe just the first case so I don't have to worry about the n's, but not a big deal. Okay. So now let's look and manage what we have. So we have n minus 1 factorial over 2 pi I integral over c. Let's multiply things out. We've got an f of zeta, which is good. And so we'll have an f of zeta. Then we're going to have to worry about this a little bit. Then we'll have a zeta minus z to the n minus 1 minus zeta minus z plus h to the n minus 1 divided by zeta minus z plus h to the n minus 1 zeta minus z to the n minus 1. Did I make an algebra mistake?
No. What happened to the over h in the limit?
Oh, good, and I have a 1 over h. Thank you. Yes, that will be very important.
So in the first line too, it should.
And the first line too, yes. And then this should also be then a limit. Equals limit as h goes to 0 equals limit h goes to 0. Okay. So now let's look at what we have over here. We have this minus this. Is the numerator large or small when h is close to 0? small. So if you look at a to the n minus 1 minus b to the n minus 1, we've seen this identity before. If you have not learned to love this identity, please learn quickly. It will make the semester much, much easier. We have two numbers, and if we look at powers of them, we can write it as a minus b, and then a to the n minus 2 plus a to the n minus 3b plus plus b to the n minus 2. And the simplest way to see this is, well, if a equals b, we have to get 0, so this has to be a multiple of a minus b. And then by doing it this way, you can have like a telescoping sum. All the internal stuff is going to cancel. So when we look at the numerator, when we look at zeta minus z to the n minus 1 minus zeta minus z plus h to the n minus 1, well, we get the difference of those. What's the difference of that? So we get zeta minus z minus minus, so it becomes a plus, or it becomes h. And now we have all this other crap, right? And what's the other crap going to be? We'll have a zeta minus z to the n minus 2 plus a zeta minus z to the n minus 3 zeta minus z plus h plus plus all the way down to zeta minus z plus h to the n minus 2. Okay? Well, now let's divide by h. And now let's send h to 0. As h goes to 0, this piece goes to zeta minus z to the n minus 2. This piece will also go to zeta minus z to the n minus 2. And the next one will go to zeta minus z to the n minus 2. They'll all go to zeta minus z to the n minus 2. So as h goes to 0, right-hand side goes to zeta minus z to the n minus 2. And how many times do we have it? I hope we have not made a mistake.
N minus 1 times?
Looks like n minus 1 times. And so, which means I am sadly off in an index by 1 unit. Okay. So unless this is supposed to be an n minus 1 factorial, unless did I drop a term by 1? So let me quickly check. I think I dropped an n minus 1. And so I do apologize. Nope. Okay. So I've got with the n plus 1 up there. So we've got we're doing things by induction. Oh wait, were you? Oh, okay. Alright, so I do apologize. Nobody caught me on the notational error. So I have an n plus 1 here, we have an n here. When we're doing things by induction over here with an n minus 1, what should the power have been over here? It should have been n. We did the power n minus 1. So we're not really taking the derivative at n. What derivative are we really doing? Right. So this is the time where we have to do quick, massive amounts of fixing. So what I need to do is I need to replace these n minus 1s with n's. So I apologize for this, but this is the advantage of being on the blackboard. So those become n's. This becomes an n, right? Or the other thing you can do is you can just change the n to an n minus 1 over there. The idea is, fortunately this time, I do apologize for the error. Right. And so now all that happens is these all get bumped up by 1. I'll wash my hands later. Okay, and so now when we do this all the way down, now we'll get an n minus 1 here, and we'll get an n over there. Alright, so algebraically, it's the same relationship, it's just changing where we're applying n to. Now let's look at what we have. We have as h goes to 0, what does the denominator go to? I'm saying the limit of a quotient is the quotient of the limits. Am I allowed to do that? You can say the limit of a quotient is the quotient of the limits as long as the limit of the denominator exists and is non-zero. Well, as h goes to 0, you get zeta minus z, and since zeta is on a circle containing z, you're fine. So when we take the limit as h goes to 0, this becomes zeta minus z to the n, zeta minus z to the n. We have zeta minus z to the n minus 1. And so when the dust settles, we get fn of z is equal to n minus 1 factorial times n over 2 pi I integral over the circle f of zeta. The h has now been played into over here. We'll have a zeta minus z to the n minus 1 over zeta minus z to the 2n d zeta. Well, now if I do the algebra correctly, the n makes this into an n, the minus 1 comes in as a plus 1, and so what happens is I can remove this factor and change this to an n plus 1. And then n minus 1 factorial times n is just n factorial. And so that finishes the proof. As n factorial is n times n minus 1. So this proves that if you are, we have Cauchy's formula, we initially only had it for the function f relating its values to an integral along the boundary. Now we have it for all the derivatives. This is amazing. Okay? Most of the time, we prove theorems in class that, fine, we've got to do something, we've got to fill up 13 weeks. This is worth seeing. This is the power of having the integral representation. The question was, how do we know that the function is continuously, continuous is better. How do we know we can keep differentiating our function? If it's differentiable once, how do we know we can differentiate it again and again and again and again and again? Well, the whole power of the Cauchy integral formula is that we can represent our function, I guess it's over here, we can represent our function as an integral along the boundary. And now notice, where is the z dependence? It's no longer in the function f. The z dependence is down here. I have to do something to justify why you come to class and not just read the book. I can spend time and I can emphasize this point. This is the key. We have transferred the z dependence from the function f to a fixed thing in the denominator, which we understand. The function 1 over z or 1 over zeta minus z, this is a well understood function. We can differentiate this function many times. Not a problem. And then we use the knowledge of the derivative of that to get the derivatives of f. This is a phenomenal trade. We've passed all the difficulty on differentiating f to here. We've now proven as a corollary that if f is holomorphic on a disk, it is infinitely differentiable. We are so close to the major theorem. Okay. Any questions on what we've done so far? Okay. So I will state this as a corollary. F holomorphic on disk, then f is infinitely differentiable, and its nth derivative, I will just rewrite it because it's so impressive it's worth writing again, is n factorial over 2 pi I integral over c f of zeta over zeta minus z n plus 1 d zeta. Okay. Does this mean that our function f is holomorphic? Yeah, well, gotcha. Does it mean our function is analytic? We want to see that these two words are the same. What does it mean to be analytic? It means you are given by a Taylor series expansion. Well, early in the semester, it was not reasonable to expect a theorem like that to hold. Just because the function was differentiable once, we didn't know it was differentiable twice or 3 times. So if you want to be given by a convergent Taylor series expansion, you need to be differentiable infinitely many times. That's the ante to even have a chance to even enter the conversation. Well, we now know our function is infinitely differentiable. Right? Now that our function is infinitely differentiable, now it makes sense to ask, is it analytic? Is it given by its series expansion? And we even know what the coefficients of that series expansion should be. What's wonderful is the way we're going to prove this is we're going to study the function 1 over zeta minus z, or powers of that. Everything is going to come from that. We're going to pass all the difficulties from f to this one nice function that we understand. I really wish I could understand like 2 or 3 functions because it would be amazing how much I can do, but this is really the only function I know. And so everything we're going to do is going to be reduced to this. All right, we're going to have an infinite series. That means we're going to want to have some way of understanding what goes on for infinite series. What's the one infinite series we really know well?
Geometric.
Geometric. When in doubt, think of the geometric. The ratio test, the root test. These are all comparison tests applied to a geometric series, where the ratio and the root test are lurking in the background, telling you, the comparison test is lurking in the background, telling you there's a secret geometric series that you're comparing this to. So we're going to somehow want to use the geometric series. So theorem. F is analytic if and only if f is holomorphic. One direction we've already done. We did analytic implies holomorphic. Differentiate inside radius of convergence. Right. That was no problem. So differentiating term by term is no problem. The other direction is harder. How do we go from holomorphic to it's given by a Taylor series expansion? Well, we at least have a candidate now for what the coefficient should be in the Taylor series expansion. They should be coming from the Cauchy formula. Since this is the only thing we know, and since I don't have as much board space as I would in 106, it's better than 103, I haven't erased this, I haven't erased this, these are probably important, we probably want to keep them here. This is why things are getting a little squished in the end. I want to keep Cauchy's formula here. Let's start off with Cauchy's formula. Alright, so we will start off, okay, this direction. So we start with Cauchy. So f of z is equal to 1 over 2 pi I, the integral over our circle C, of f of zeta over zeta minus z to zeta. And we want f of z to be a sum of an z minus z naught to the n. N goes from 0 to infinity, z naught inside c. So I want to be able to say I can expand it in a series about a point z naught. And if so, then I can relate f of z to the sum. I don't have a z naught here. Does everyone agree we want a z naught? How can I get a z naught? We've already used this idea today. How can we get a z naught?
Do nothing.
Do nothing. Good. How do you do nothing?
Multiply by 1.
So we could multiply by 1, and then we'd have a z naught over z naught. How else could we get a z naught?
Plus subtract.
We could add and subtract. Where do we want to add and subtract a z naught? Because remember, we're going to want to look at things, z minus z naught. Where do you think you want to have a z minus z naught? Where's that lurking? Denominator. So 1 over zeta minus z is equal to 1 over zeta minus z naught plus, minus z minus z naught. Now, because the minus and the minus is a plus, the z naughts cancel. So the reason I want to write it like this is z is supposed to be very close to z naught. This is supposed to be very small. And now we've brought z naught into the problem. Again, we have this integral formula. This relates the values of f to an integral of f on the boundary with no z dependence. The only z dependence is down below. We want to keep the z dependence away from f. This is the same as 1 over zeta minus z naught, 1 over 1 minus z naught over zeta minus z naught. And we'll try to write cleanly. And all I'm doing here is I'm just pulling out the zeta minus z naught. Why am I doing this? I now have 1 over 1 minus blah. Does that look familiar? Yeah, this is the... It's some of the infinite geometric series. So this expression here is just 1 over zeta minus z naught, and then we have a sum, n goes from 0 to infinity, of z minus z naught over zeta minus z naught to the n. Why am I doing like this? Well, I've got this extra factor of zeta minus z naught. Let's just bring that inside the sum. And so this is now the sum, n goes from 0 to infinity, of z minus z naught to the n over zeta minus z naught to the n plus 1. I am trying to, actually this is fitting as before the Day of Atonement, I am trying to make up for my algebraic mistake earlier today where I had the n and the n plus 1 wrong. I think right now I've got the n and the n plus 1 correct. Is I have one higher power down below than I have upstairs. And if you look at the Cauchy formula for the nth derivative, which is still staying on the board, we can see this is exactly what we're going to want. We have a zeta minus z to the n plus 1. Well, okay, f of the nth derivative at z is equal to this. Well, now if instead of z we have zeta, that's not a big deal. So now we'll use, and I just have to replace z with z naught. So I'll erase this and give you a moment to just rewrite this. So we're going to use that fact. We're going to use Cauchy's formula applied to the point z naught to get us the nth derivative at z naught is this integral. Well, we're not going to have the n factorial, so what we'll probably do is it's probably a little bit better to rewrite it like this. Okay? And now, what do we have? We have f of z is equal to 1 over 2 pi I, the integral over c. We have f of zeta over zeta minus z, so that became f of zeta, and then we have a sum, n goes from 0 to infinity, of z minus z naught to the n over zeta minus z naught to the n plus 1 d zeta. Okay, this is just substituting everything in. What would you love to do at this point? What would you love to do? You should be restraining yourself from doing this right now. What is your natural instinct to do at this point?
Change the sum.
Of course, right? You should be furious that I'm not letting you interchange the integral and the sum right now. Then we'd be done. We want to say the integral of the sum is the sum of the integrals. We can then pull the z minus z naught outside the integration. And then we would basically be done, and we would have our series expansion. And the ANs would basically be like the nth derivative over n factorial. So all we need to do is to justify interchanging the sum and the integral. So done if the integral of the sum is the sum of the integral. There are several ways to justify this. I will show you a clip of Cameron when he was 2 years old with his magic bubble wand, which allows him to interchange sums and integrals. Most people do not have magic bubble wands, unfortunately. Yes?
Can you just go over once again how you went from the first line to the second?
From this line?
Yeah.
No, I'm saying we're going to use this.
Oh, okay.
This is going to, we then use this over here, because once we interchange the sum and the integral, then we'll have an f of zeta over zeta minus z naught to the n plus 1. And then using above gives f of z would be the 1 over 2 pi I, this and this and this would all give us the fn of at zeta naught over n factorial. So we get a sum, n goes from 0 to infinity, of the nth derivative at z naught over n factorial z minus z naught to the n. And that would finish the proof, once we can justify the interchange. So we then use that, and we can interpret this. And if you check you're always wondering, am I supposed to have the n factorial here? If I differentiate this n times, I get an n factorial from that, which cancels with that. It should, yes, it should have an n factorial here if I'm writing it like this. So everything is all set if we can justify the interchange. Okay, so we have 5 minutes left. That should be more than enough time to do things rigorously. Okay? So it all comes down to, can we justify the interchange? The important thing to note is we have moved all the action away from f. We're not evaluating f at z anymore. The z is in a very special place. So we have 1 over 2 pi I integral over c f of zeta f of zeta, the sum, n goes from 0 to infinity of z minus z naught to the n over zeta minus z naught to the n plus 1 to zeta. And I'm going to look at the absolute value of this. If I can show that the sum of the absolute values is finite, we can interchange. That's essentially Fubini's theorem. Okay? So this is going to be less than or equal to the integral over c, the absolute value of f of zeta, the sum, n goes from 0 to infinity, z minus z naught to the n over zeta minus zeta naught to the n plus 1 d zeta. And now, let's draw a picture. So maybe here is z naught. We don't even have to have z naught at the center. Here's the center of the circle. The circle has radius. The circle has some radius, we'll call it r. Zeta lives over here. Here's z naught. Here's z. The first thing we'll do is we're going to make sure z is damn close to z naught. And what we can do is we can make sure it's much closer to z naught than z naught is to the boundary. Things are a little bit easier if I make z naught be the center. I don't need to. Let's let little r0 be the minimum distance from zeta to z naught, zeta on boundary. Choose some h such that z minus z naught is less than or equal to h, which will be less than r naught over, it's 2015 or 2015. Does the number 2015 matter? I'm just putting in a large number just so that you know I'm just choosing things that values don't matter, I just need something big. The point now is z minus z naught is going to be much smaller than zeta minus zeta naught. And now when I look at what's going on here, and I want to see how big this is going to be less than or equal to the maximum of f of zeta, zeta on c. So I can just pull that bound outside. I have a sum, n goes from 0 to infinity. Zeta minus z naught is going to be at most h to the n, and this is going to be at most naught to the n plus 1. That series converges, because h is smaller than r naught. Converges. So, can use Fubini. So the integral of the sum is the sum of the integral. And that finishes the proof. Okay? So, there's a lot of technical stuff today. Most of it came from doing nothing. That's one of the good things. There's really not that much to learn. What you need to know is you need to know when do you want to appeal to different things, when do you want to use different facts. And so again, there's a lot more in complex analysis we can do. Please send me feedback. Am I doing a good job of juggling how much detail to go into? When am I leaving things in the book for you to look at? And when am I trying to emphasize things? I want to try to emphasize, why do you use this inequality? We've used a to the n minus b to the n many times. The whole point here, the whole story of today is we want to move the action. We want to move the action to a very nice local place that we can understand. And then by understanding what's happening with f elsewhere, we can then figure out what's going on in the places we care about. Okay, so this is a good place to stop, and then we will look at consequences of this on Friday. How many of you have seen the fundamental theorem of algebra? It's basically one line away. We are one line away from that proof.